Well, okay. Let me correct the organization here of this chapter, okay? The section number that I was using yesterday was the section number of another edition of Holiday Resnick. Looking here at the ebook of yours, let's take a look at the exact, sections that we have in there. Okay, we covered 33.1, which is electromagnetic waves. Let's see here. Yeah, 33.1. Here you go, electromagnetic waves. Energy transport and the Poynting vector is 33.2. We covered that as well. We covered 33.3, that's radiation pressure. We didn't cover polarization yet. I like to cover polarization afterwards. Then we went into reflection and refraction, what I also call geometric optics. Total internal reflection. Okay. And then there is something else that I want to cover here within. Wait a minute. There's something else I have to cover here. That's dispersion as well. That I didn't do last time. Okay, reflection and refraction. Let's see here. Reflection and refraction. Blah, blah, blah. Yeah, here you go. That's dispersion. Chromatic dispersion. Okay, that's in reflection and refraction. I did cover total internal reflection. I'm gonna put here in boldface what I'm gonna cover today. And we have to cover those other two topics, polarization and reflection by polarization. Okay, so let's talk about dispersion that I didn't talk yesterday. Dispersion. What's dispersion? What is dispersion? Well, dispersion is the refraction of light at different wavelengths. Okay, so far we have assumed that every wavelength is refracted in the same way. But in reality, that's not so. But in reality, that is not so. Okay? Depending on the wavelengths, light is going to be refracted differently. And that's because, each wavelength sees, right, a different refractive index in the medium. So what is diffraction, dispersion again? Dispersion is something like that. It can be summarized in a mathematical formula. Dispersion can be summarized in the following mathematical formula. The index of refraction of a given medium is actually a function of the wavelengths of the light. Okay, that's how you can summarize it. Many, many optical materials have their refractive indexes written in terms of the wavelengths. And it is this type of phenomenon that is responsible for the rainbows. For the rainbow we see every now and then, right? That's what dispersion is all about. Okay, so because the refractive index of a medium varies with the wavelength. What does it also mean? This also means that different wavelengths have different speeds in this same medium, right? Remember, the refractive index is given by what? It's given by the speed of light in vacuum. That doesn't depend on the wavelength, divided by the speed of light in the medium. And consequently, this speed of the light in the medium is going to be a function of wavelengths. It's like that. So that's a piece of information you have to know. And let's take a look at the book. So here we go. Here's an illustration of dispersion and prisms. They disperse light. Oh, here you go. That's what I want to show you. This is the type of information that manufacturers tell you about the dispersion properties of their own optical materials, okay? Here goes, chromatic dispersion. That would be a better way of expressing it. It's chromatic because chromatic comes from the color of the light related to the wavelengths, okay? So here you go, the index of refraction goes down with the wavelengths, okay? Refractive index is larger at shorter wavelengths. Blue, blue light see a higher refractive index than red light and infrared light for this specific optical material. Let's see if they document as quartz. That's for fused quartz. Okay. Index of refraction is a function of wavelengths for fused quartz. So because the refractive index as seen at the shorter wavelengths is higher, it means that shorter wavelengths are bent more than longer wavelengths. Let me show when it refracts through the material. Okay, so here you go. Here's an illustration. White light is a combination of every possible light color. Okay, it's made up of blue, green, red, and everything else in between. Okay, so when you shine a white light beam at the surface of a dispersive medium, each of those wavelengths are going to travel at different speeds, and they're going to be refracted differently. So the medium causes each of those wavelengths to be dispersed, to be separated. And it forms the typical colors of the rainbow when something like that happens. Okay, let me see if I can get, let's see. I'm going to elaborate a little bit more on this drawing. What happens to this light? Oh, interesting. Here you go. What happens to this light when it gets, whenever it refracted out into the air, right? So here you go. Each one is going to refract away from the normal. You know, let me see. Let me get something else here. Here you go. Here's the normal direction, right? So here you go. If there is no refraction, the blue light would travel in a straight line, right? But because there is refraction, blue light is going to bend away from the normal. Same thing happens here with the green light. Here, if there is no refraction, right, it will travel unbent. Okay, but because there is refraction here, the amount of bending is going to be dependent on the angle of incidence. Because similarly here, no refraction, red light, you know, moves away like that. But with refraction, red light bends away from the normal. That's why you can see the colors of the rainbow, because of the presence of a chromatic dispersive medium. And the amount of bending is going to be dependent on the material and how dispersive it is with respect to each wavelength. That's the case of quartz. Those things can be measured. Okay, the variation in the refractive index, you can see in this case, goes anywhere between 104.55 all the way up to 1.48. Here is where we start to get into UV region, the region of UV light. So we're talking about 0.03, right? 0.025, which is a large variation refractive index. Consider a large variation refractive index. Okay, so that's what you have to know about dispersion. It's not always like that, okay, because it depends on the medium. Let's take a look at some other types of glasses, okay? There are dispersion by different glasses. Let's see here. Measure for dispersion. Let's see this one here. Yeah, here you go. Not just different types of glasses, but different types of optical material. Here you go. Here is the dispersion curve for fused quartz, like the one you saw in there. And here's for acrylic, the plastic that we buy out there. And here's for a type of glass that we call crown glass. All those three materials decreases with the refractive index decreases with the wavelengths. We go medium. Okay, so when you buy eyeglasses, okay, you can, just like me, right? When you buy eyeglasses, you can buy eyeglasses made of different materials that has a higher or lower refractive index. Glasses that have a higher refractive index can be made thinner because it refracts light more strongly. Lower refractive index materials, you know, has to have a very thick lens in your eyeglasses. Okay, so let's see if we can get something else. There are some optical glasses out there. Oh, here you go. Here you go. I like this one. Dispersion optics. Let's see. Here you go. Those are different types of materials again. Here you go. Flint F2 glass. Here you go. I like this one. I like this one because it gives you the dispersion of different glasses of a manufacturer. Those glasses that you see here, let me see, it seems to me that's a shot glass. Shot glass has those types of glasses. Shot glass is a German manufacturer of glass. Let me see if they say anything about shot glasses here. Here you go. Shot. No, he doesn't have. Well, most likely it's shot glasses. Yeah, most likely shot glasses because it's the same notation that shot uses in their different types of glass. LASF9, for instance, F2. I used to buy those F2 glasses from Shot to make optical fibers. BAK4. I used to have their shot glasses. Shot glass publish a huge catalog with the optical properties of their own glasses, documenting many things, among them the refractive index variation with the wavelengths. This Wikipedia article doesn't say who those glasses are, but most likely it's shot glass. Fluoride crown, this variation here. But in general, not all the time, in general, wavelengths decreases. In general, index of refraction decreases with the wavelengths. And we have here the visible region between 400 and almost 800. And that's infrared, that's near infrared, that's near UV. Okay, the wavelengths of visible light are shaded in gray, right? That's the visible wavelengths region. So you can say that in general, the refractive index decreases with the wavelengths. Okay, is an inverse relation. In general, not always like that, because there are some regions of the electromagnetic spectrum that's going to behave differently, but we're not going to cover that for the sake of this course. Okay, for the sake of this course, it's okay to believe that in general, the refractive index decreases with the wavelengths, And that's what dispersion is. Going back here to our, here you go. No, not this one. And by the way, if you notice, I have already posted all the homework there for you, okay? Let me know if you, oh, I didn't publish it, this one. Yeah, okay, now I published. Make sure you can access this homework. Okay, and here. What else? Go. Blue light is bent more steeply because it sees a higher index of refraction. The rainbow balls is that you see is due to dispersion, chromatic dispersion. Okay, that's here an explanation of we did an example of refraction, right? And here's we're talking about refraction of a monochromatic beam. That's what we assumed last time. But there is this small correction. We call that a first order correction due to the wavelengths, which is chromatic dispersion. We did an example like that, right? And we did the total internal reflection as well. Okay, here goes same illustration that I showed to you, right? If you are underwater, oh, either if you're underwater or if you have a source inside the glass, you can have total internal reflection, okay? And here you go, here's an actual picture of a light source submerged in water. Oh, well, let me see, in glass, he said in glass. Yeah, okay, so what he's doing here. Okay, so you, in glass, for all angles of it. I wonder how they put a source there inside the glass. Interesting. Okay, so he's changing the angle, right, of incidence here on this glass, and eventually you have total internal reflection. That's something that happens in real life. Okay, I have something similar in my website. A little bit more complicated, but it also gives you, it also shows you okay, you saw this one before, right? In this case here of this light beam is not undergoing total internal reflection. You can see it that the light leaks out, right? You have partial internal reflection. That's because this angle here is not greater than the critical angle, right? But if you do something else, and by the way, that was a patent of mine, okay? If you, instead of having a bar with parallel sides, you get like something like that makes an angle, right? A wedge, like a wedge waveguide. If you illuminate from the outside, you're going to see the light being refracted here. But when the light is incident at the surface, don't forget the angle of incidence is measured with respect to the normal. If this angle is not greater than the critical angle, you're going to have some of the light leaking out, okay? But because of the nature of this wedge, every time that there is a reflection at the surface, the angle of incidence changes, becomes steeper and steeper, okay? Eventually, what happens? You end up having total internal reflection. This pointing around this point here, you already have total internal reflection, okay? And that can be nicely imaged with this special type of glass. This light that you see here is reflection from the surface, partial reflection from the surface, refraction, light leaking out, partial reflection, right? Eventually the light, because of the angle that you have here, lights eventually start undergoing total internal reflection. That's another way of illustrating total internal reflection. Why is total internal reflection is important? Total internal reflection is important because if you have total internal reflection, very little light ends up leaking out from this device that we call a waveguide. And total internal reflection is used to transmit light over thousands of kilometers, especially using those ultra low loss glasses that we have out there. Okay. If you go back to my other, here you go. Here is a illustration that I showed to you that's also in the book, right? You can illustrate, you can think of that, this medium as being water. Eventually, you're going to get total internal reflection depending on the angle that is incident here at the surface, right? And then how we can illustrate propagation through what we call a waveguide, right? If you have the right angle, here you go. This light here can be propagated almost indefinitely with very little loss. Every time that the light is incident at an angle smaller than the critical angle, you lose some light, you lose some power, okay? So if you want to do telecommunications using light for longer lengths, you have somehow to inject light into your waveguide that will undergo total internal reflection. Okay, we go. And let's see, y plus critical angle. Okay, what's the condition for critical angle? Remember the condition for critical angle. I'm just remind you, right? Condition for the critical angle is, you know, theta of refraction is equal to 90 degrees. Okay, theta 2. Let's copy that. If condition for the critical angle is, you know, theta 2 equal, you know, to 90 degrees, where this theta 2 is the angle of refraction. Here you go, refraction, not reflection, but refraction. Okay, when theta 2 is equal to 90 degrees, okay, when the above condition is satisfied, then theta 1, or the angle of incidence, okay, becomes equal to the critical angle. The critical angle, and the critical angle is going to depend on the relative refractive index of the medium, of the true media. Something that we did before, right? This Snell's law, apply this special condition for the critical angle, and we can find out the critical angle. Did we do? Here we go. Same thing. Here is the, let's take a look at this example. Here you go. When light reaches the interface between two materials, different degrees of refraction, and one part of the light is reflected, right? The reflection is total. If the incident light being the material with a higher index of refraction, the incident light is in the material is a higher index of refraction. That's the condition, two conditions, right? That you're going to have total internal reflection. The medium, you know, medium 1 condition, let's write that down here. The both condition N1, the both conditions satisfy. Let's see, condition for critical angle. Okay, total internal reflection occurs only when light goes from a medium of higher refractive index to a medium of lower refractive index. And what does it mean? Here you go. I'm going to write down here. N1 greater than N2. That's, if you don't have this condition, you're not going to have total internal reflection, okay? But still, to achieve total internal reflection, you must have this other condition, two conditions, right? Two conditions for total internal reflection. Two conditions for total internal reflection, PIR. One, light must go must propagate from a medium of higher refractive index towards a second medium of lower refractive index. Okay. Two, the angle of incidence measured with respect to the normal to the surface must satisfy the following must satisfy these additional conditions. The additional conditions. Okay, here you go. A. The theta 2 must be equal, theta 2 it is equal to the theta angle of refraction, right? Theta of refraction must be equal to 90 degrees. And applying this condition to Snell's law, let's put that between quotes. We have theta 1 equal to theta incidence is equal to theta critical. We have, you don't need to put like that. Here you go. And let's see here. Good. In Snell's law, that's the case. If n1 is greater than n2, this ratio is going to be less than 1, which is satisfied by the behavior of sign, right? Sign cannot be greater than 1. That's total internal reflection. And now let's talk about polarization. Let's go back to 33.4, right? Here you go. What's polarization, right? 33.4, polarization. Okay. So far, I introduced you to a special type of polarization. Okay, so let's see what's polarization first. Here you go. What is polarization first, right? You gotta know what polarization is. What is polarization? Polarization relates to the direction of the electric field of a light beam. Okay, that's what it's all about. That's what polarization is all about. Remember, electromagnetic waves are made light in electromagnetic light, which is an electromagnetic wave. Magnetic wave made of electric and magnetic fields. Okay. In free space, okay, E is perpendicular to B. Okay. When you were talking about wave, guys, the situations are likely different, but you don't need to know that. Okay, so here you go. If the electric field is oriented in a single direction, right? We say that the light is linearly polarized. Okay? And you saw an illustration like that before, right? So here we go. We represent a linearly polarized light in the following way. You already saw something like that, right? So, but let's just remind you of that. This is gonna come later. I usually cover polarization at a later stage, you know, this book okay, here you go. Here's the illustration of an electric field, right? It should describe a sine wave. Let me get that a little bit higher, right? Like that. It should describe a sine wave. If this electric field points only along the y direction, we say that this light is linearly polarized. Remember, in order to picture light, you have to picture electric and magnetic fields, right? So if you have the electric field in this direction, you're going to have a magnetic field pointing perpendicular to the electric field, so you're simultaneously perpendicular to the electric field and to the direction of propagation of the light. In this specific case, the light is propagating from the left to the right, just according to the right-hand rule of the Poynting vector, right? E cross B. Here you go, direction of propagation. Direction of propagation. Direction of propagation, the ENM wave. Okay, and here you go. Here's the magnetic field tagging along the electric field, making an angle of 90 degrees. I'm going to put it in different colors so we can distinguish. Red color, okay? We can distinguish from the electric field more readily. At this point right in here, both the electric and magnetic field are zero. Okay. And then the electric field is reversing direction. So will the magnetic field. Here you go. Right in that. So that's x-axis. Let's see, x, y-axis. Let me put here y-axis here. This field is propagating along the x-axis. Here's the y-axis. The electric field is the electromagnetic wave is propagating along the x-axis. The electric field is pointed along the y-axis. The magnetic field is pointed along what? The z-axis, right? The z-axis is going to be like that. Z-axis. I don't need that, but I'm going to need that. hopefully you have the illusion that is, electric and magnetic fields that vary in time and position. Okay, this is considered what we call linearly polarized electric and the electric field and B field. Okay, you get the idea? As time goes by, this arrow is pointing up and down, up and down. Okay, in real life, most of the electric field is not linearly polarized. Okay, so in real life, most of the E fields that we see out there, are not polarized. Okay, we say they are randomly polarized. And what does it mean? What does it mean by electric field being randomly polarized? Here you go. That's how we represent a linearly polarized electric field. Now I'm not going to talk about magnetic field. I'll just concentrate on the electric field. Okay. Here is an electric field that's polarized along the vertical direction. Here's another electric field that's polarized along the horizontal direction. Okay. And you can have an electric field polarized along the Z direction. Okay. Okay, in general, you do not have something like that. In general, you have an electric field that's randomly polarized. It oscillates in this direction, oscillates in this direction, oscillates in this direction, and so on. Okay? Because the electric field is a vectorial quantity, we can sum all those vectors to come up with a direction, a net direction that's going to be 45 degrees of the electric field, okay? Because of the random polarization, right? Because of the random polarization of the electric field, the magnitude along this direction is going to be equal to the magnitude along this direction, the magnitude along this direction, and so on. Overall, what you end up having, and when you sum everything vectorially, you end up having something like that, that makes an angle of 45 degrees, okay? You go, I'm gonna put here the vertical direction for you. Here you go. Net direction of polarization. I'm gonna put like that. Net direction of polarization of the light. Of a randomly polarized light. Okay. Can you picture that? So going back here to the linearly polarized light, okay? Here you go. Okay, there are materials out there that can change the state of polarization of the light. Okay? They actually filled up as a polarization filter. Filtering out electric fields. that are oscillating at directions other than the polarizer itself. So what a polarizer are? There are filters. There are polarization filters. They let light, in other words, they let only light of, they let only E fields of a certain polarization to pass through it, okay? So let's say, example, okay? Let us say that a polarizer has a polarization axis along the Y direction. You can buy those materials out there. And by the way, some eyeglasses, they act like polarizers, okay? Sunglasses, not eyeglasses. Some sunglasses act like polarizers. We can write that down here as an example. As an example, you know, sunglasses, depending on the sunglasses, by the way, depending on the sunglass you use, comma, they act as a polarizer, as a light polarizer. So let's say, you know, example, let's say a polarizer has a polarization along the Y direction. And you have, you know, if you have the electric field of a source linearly polarized along the Y-axis, okay, all the light of this electromagnetic radiation will pass through this polarizer. Okay? How do we illustrate that? We illustrate that in the following way. Here we go. Let's see here, this one, right? So I'm going to illustrate my polarizer with a red arrow. Okay, here we go. Polarizer. What you see here is a polarizer. Put it in red color. Here you go. Electric fields that are polarized along the Y direction is gonna pass through this polarizer without being filtered out. Okay. Linearly polarized this field, linearly polarized this field along the Y direction. Polarizer also along the Y direction. Okay, so here you go. If I were to, I'm gonna put that here. I'm going to, here you go. We can, if you use this one, I'm going to make a little bit thicker so you know it is in there. Here you go, better, right? If field and the polarizer, here you go. One more. They are oriented in the same direction. Make it thicker here too, right? To be consistent with what we have. This dot that you see in there is the magnetic field, right? That's tagging along with the electric field. Send to back. Here you go, electric field. Now, what if the electric field is oriented in a different direction? What is the electric field is oriented now in the y direction? Okay. Linearly polarized E field along the x direction, polarizer along the y direction. Y direction. Here. So what's going to happen here in this case? No electric field goes through, and I represent that by a dot. Okay. No electric field goes through. So here you go. Let me represent here this electric field along the direction perpendicular. Okay, that's before. I'm gonna put that before passing polarizer. Before polarizer. E field before polarizer. E field after polarizer. So we go. E field after polarizer. So it becomes a dot, means that the electric field is 0. The polarizer filtered out completely the electric field. Okay. Now there is everything else in between. Okay, you can have E field making an angle. X and Y component, with the X and Y component, linearly polarized field along X and Y directions. Okay. Polarizer. So we can have the combination as well. So it would be something like that. Here you go. My electric field now is making an angle with the polarizer, and I'm going to document this angle as being angle theta. Make it a little bit longer. Oops. Angle here, I'll call that angle theta. Okay, make it bold-faced. Then what happens? E field before polarizer, only what is only that field that's parallel to the direction of the polarizer survives. Here you go. I'm going to project. Now do you see how important it is to understand the vectors, right? We apply that all the time. Here you go. Only what is parallel to the direction of the polarizer survives. here, and here. I'm going to do even better. I'm going to make it a dashed. Here you go. This one like that? Yeah, let's do like that. Better. And now the resulting vector is going to be this one. The resulting electric field is going to be this one. Okay. Here's the angle theta. So if you had an amplitude E naught here, right? What's left over is a E naught cosine of theta. Okay, so here you go, going back here. Let's say that the polarizer has a polarization axis along the y direction. If you have the electric field of a source linearly polarized along the y, all the light of this electron will pass through the polarizer. Okay. Okay, another example. All the light, electric field. Another example. Here you go. Example 1, example 2. Let us say that a polarizer has polarization along the y-axis. If you have an electric field of a source linearly polarized along the x-axis, all the light of this electromagnetic radiation will be filtered out, will be blocked or filtered out by this polarizer. In this case here, okay, we say that the final, in the first case, right? In the first case, we say that the final, here you go, I'm going to use this one. Here you go. In this case here, we say that the final intensity, here you go, we say that the angle of polarization between the light and the polarizer is 0 degrees, okay? And what passes through the polarizer is the same electric field that you have before. And the final intensity, remember the intensity is always the square of B naught, is going to be equal to the initial intensity. Okay. Similarly, here you go. If you have an angle now of 90 degrees between the direction of the electric field and the direction of the polarizer, the final electric field is going to be 0. And the final intensity is going to be 0 as well. Okay. Don't forget the final intensity is going to be equal to E squared, right? That ends up being equal to 0. Now, what about example 3? A more generic case is in which linearly polarized if you have the electric field making an angle theta with respect to the polarizer axis, right, of the light of this electromagnetic radiation will be blocked or filtered out by this polarizer. Here you go. Symbol. Here you go. Now I want to put a theta here instead of Okay, that's what the final electric field is going to be. When we take the final intensity of the light, we get this relation here. E naught square cosine square of theta. That's for, that's for light that is linearly polarized. Okay. What about light that is randomly polarized? Okay, and what does it mean, random polarization, right? First, what does it mean to be randomly polarized? Okay. Okay, randomly polarized means that we have electric fields at every possible direction with equal amplitudes, okay? And that was the illustration that I did before with equal amplitude, right? So that's the illustration I did before. Here you go. Randomly polarized. Here you go. Not only I have electric fields along the vertical direction, I also have electric field oscillating along the horizontal direction. And the amplitude of this field, the vertical direction, is the same, the amplitude of this field, horizontal direction. And we have electric field oscillating also at the other angles. Everyone having the same amplitude. That's what randomly polarized is all about. Okay? For this type of polarization, the net polarization is going to make an angle of 45 degrees with the vertical direction. Make sense? Which, if you sum vectorially all possible electric field vectors, it's going to make an angle of 45 degrees. Okay? If you go, so example 4 now, right? Example 4 now. Let us say that a polarization has a polarization axis along the y direction. Same case. If you have an electric field with random polarization, what is the final intensity of this field after passing the polarizer? That's the idea here. Okay? And I'm going to put a solution. Let's finish this one and you go for our break, okay? 9:06 already. So again, here you go. If you have this random polarization here, if you sum all those vector electric fields vectorially, you're going to get a net direction polarization that's 45 degrees. You know what? I don't think I need this one. I'm gonna get this one here. Here you go. Here you go. 45 degrees right in here. Superscript, here you go. And let's make it thicker too, right? Just like we did before. I'm gonna make it a little bit bigger too, longer. Okay, here you go. Net randomly polarized electric field. Then there's the net the direction of the net polarized light, of the net polarized light, of the net randomly polarized light makes a 45-degree angle with the vertical. Like that. Okay. What does it mean? Okay, what survives is going to be just like we did before, right? Here you go. Okay, so let's use this one, huh? So we have it. Yeah, let's use this one here. Right? Yeah, here you go. Going to the front. Before E-field, before polarizer. Get rid of that. We don't need that anymore, right? Makes a 45-degree E-field after polarizer. And now we can calculate what's going to be the intensity, right? Just like before. We know the angle. All we have to do is to use this equation right here. Here you go. Solution. Initial intensity is E naught square. It's proportional, right? We say that's proportional. Here, what we have is 45 degrees, which, by the way, oh, I have it here. Yeah, I already have everything done here. Is square root of 2/2. The electric field has this amplitude, but the intensity, what's going to be the intensity? The intensity is going to be half of the initial intensity. Okay. That's what we have for polarization. Make sure you understand this idea. To go, the book doesn't explain how he got that, okay, but that's how you picture the randomly polarized light. Okay, there, here you go. He says something about the invention of polarizers. Okay, let's see. Let's look at that here. Key ideas. Just invented that. It was in the other one. No, no, it was in this one. Polarization. Let's see. Okay. Plane of oscillation, polarized light. Polarizing. Okay, here you go. Polarizing direct. We can transform unpolarized visible light into polarized light by sending it through a polarizing sheet. Okay, as is shown in figure 33.4.3. You go, before passing through the polarizer, after passing through the polarizer. Okay, such sheets, right? Commercially known as polaroids or polaroid filters. Remember I said that polarizers are act like filters. They were invented in 1932 by Edwin Land while he was an undergraduate student. Isn't that nice? You know, you're an undergraduate student and you invent something important that's used today. Oh boy, my cat is meowing out there. Okay. Okay, so here you go, here's the intensity, and that's what we have. We covered all of that. Let's have our, before I go for our break, let's take our attendance here. The 28th. Toby, are you there, Toby? Toby. Okay, Toby is not answering. I'm going to put a star here for him. Harun, are you there, Harun? Harun Atif. Let's see, Harun. Yeah, Harun is here, but is not answering. Oh, yeah, he's answering. Okay, thank you. Musa, are you there? Yes, okay, good. Zachary Blue, are you there? I can see Zachary, but I don't hear from him. Okay, I'm gonna put a star here. Elena, are you there, Elena? Good, next. Crystal, are you there? Don't hear, don't see Luis Crystal. I don't see Crystal here. So goes to 0. Brian Spino. Brian, are you there? I don't see Brian either. Robert Faust, are you there? Pedro Flores. Good. Lawrence Flores.
Here.
Daniel Freire. Daniel Freire. I don't see Daniel here in my list. Amalia Gale.
Here, Professor.
Thank you. Tiffany Wang. Good. Olivia Kruger. Daniel Liang. Are you there, Daniel? Let's see if Daniel here is in my list. Yeah, I see Daniel here, but I don't hear from him, nor any messages from him. He goes, Sarina, are you there? Good. Anthony Lopez. Next is Chuck Lu. I see Chuck here, but I don't hear anything from her. So he goes. Dave Dimaez. Next is Ryan McNeil. Next is Alexis Nigret. Alexis, okay, good. Alexis here. Daniel Nwagbo.
Yeah.
Good. David Nwagbo. Good. Next is Claire Ottinger. I see. Good. Thank you. Jennifer Ramirez. Jennifer is here. Noah Raymond.
Here, Professor.
Thank you. George Risk. Let's see. George is here. Good. Safi. Natalie Santiago.
Here.
Nathan Silva. Good. Next is Darnice Simon. Next is Kenny Villagomez.
I'm here, Professor.
Thank you. Nolan Williams. Okay. And Meng Shu. Are you there, Meng Shu? I see Meng Shu there, but he doesn't answer. Let's see, it's Olivia Song. Are you there, Olivia? No, Olivia stopped coming. It says we have, okay, so let's go. That's 9:17 now. Let's go for a break.
Professor?
Yeah.
This is Zachary. I'm here.
Zachary. What's the last name?
Blue.
Zachary. Blue, okay.
Oh, Professor.
Toby, are you there, Toby?
Yeah.
Okay. Daniel Liang, are you there, Daniel Liang? Okay. Chuck Lu, are you there? Yeah, Chuck's not answering, right? Check is no longer in my list. Okay, so it's gonna be a 0 here. Good. And Mengshu? Mengshu not answering. Yeah, okay. 29. We have 31. Okay, so let's go ahead and have our break. It's 9:18 and the break's gonna be until 9:33. Break to 9:33 a.m. Okay. Talk to you soon. Okay, now I'm going to start sharing the screen again. Let me show you how light passing a polarizer looks like, okay? Polarization. Here we have a picture of a polarizer, actually two polarizers. This real life picture. We have some of those there at the college, some of those polarizer slides. Take a look at, we have this polarizer here and this other polarizer. This red line indicates the direction of polarization, the direction of the polarizer. Okay, and then we have this piece of paper here that is emitting unpolarized light. Because this light emitted by this piece of paper is unpolarized, the first polarizer filters out some of the light. That's why it looks like a little bit darker. Okay. Now, because the axis of polarization of the second polarizer is in the same direction of this one, whatever it's seen here in this region is almost the same as what you see it here in this region, right? However, if you rotate this polarizer, what happens? Here you go, see? Rotated by 90 degrees, then it becomes completely dark. It doesn't let any light pass through because the axis of polarization of this one is making 90 degrees with the axis of polarization of this other one. That's exactly what happened in real life, okay? And what we want to do now is last reflection by, no, it's not reflection, reflection is this one here. The last section of this chapter, 33.7, polarization by reflection. Let's take a look here at our notes. We go, that's where we started. We did polarization. Now we're going to do reflection by polarization. What we discussed so far is just polarization by transmission, okay? Let's write that down. Polarization by transmission. Transmission means you pass light through the device to polarize the light. But you can also polarize light by reflecting it out of a surface, okay? So polarization by reflection, right? 33.7. Yeah, 33.7. Polarization by reflection. What we saw before is polarization by transmission. We pass light through a polarizer and the resulting light becomes polarized. Okay. Another way to polarize light is by reflection. Okay. So let's review quickly. There is what we call a Brewster angle. If we illuminate the surface, if you illuminate a given surface at a given angle, at a special angle, which is called the Brewster angle, the reflected light is going to become polarized, okay? It's possible to do that. And this angle, the Brewster angle, must obey a certain condition here. What's this condition? The condition is that the refracted light and the reflected light must make an angle of 90 degrees. Okay? If this condition is satisfied, the reflected light becomes polarized. Not the refracted light, not the refracted light ray, but just the reflected. So this light becomes polarized, but this one doesn't, right? Continue like unpolarized. So here you go, a ray of unpolarized light in air is incident on a glass surface. Doesn't have to be glass, can be water as well. Okay, at the Brewster angle of theta b. The electric fields along that ray have been resolved into components perpendicular to the page, the plane of incident, reflection, the components parallel to the page. And components parallel to the page, right? Perpendicular to the page is the yellow one, parallel to the page is this one here. Okay, so unpolarized light in every possible direction here, parallel and perpendicular to the page. Okay, and the light is polarized along this direction here, along the direction that's parallel to the air glass surface. Okay, notice that this component here is not parallel to this interface. What ends up being polarized is this component that's reflected, and the direction of the polarization is going to be parallel to the air glass interface. Can you remember that? Okay. The component that's perpendicular to the page is also parallel to the air glass interface, to the two medium. Okay. So here I'm just telling you that that's the condition for reflection under polarization. I'm not proving that mathematically. We don't do that here at this level. Okay, but that's something that's very easy to remember, right? So two important angles. Remember, two important angles is by reflection. Okay, another way to polarize light is by reflection. If light is incident at a special angle that we call the Brewster angle, the reflected light will be polarized in a direction that is parallel to the interface of the two dielectric media. Okay. The condition for the Brewster angle is satisfied according to the equation, right? Let's take a look here. Let's go back to the drawing again. Here we go. See, that's the Brewster angle. Angle of incidence is equal to the angle of reflection, right? Since this one is the Brewster angle, this one is also going to be the Brewster angle. So when this angle here is 90 degrees, we have the Brewster angle. Okay. So go ahead and here you go. This, this angle here is gonna be 90 minus theta of refraction. right? And this angle here is going to be what? 90 minus theta Brewster angle. So how do we do that? Just memorize this figure, and then if you forget the condition, you can refer to the figure, right? How it is, okay, according to the equation. So here go. Ninety degrees minus theta Brewster plus 90 let's see here. Let's do that again. Theta Brewster. Oh yeah, here you go. If this angle is 90 degrees, right? This one plus this one is going to be 90 degrees as well, right? Here you go. There's a better way of doing that. Theta Brewster plus 90 degrees plus theta R. Okay, so yeah. Yeah, it's better to do this way. Theta Brewster plus 90 degrees plus theta R is 90 is equal to 180. Okay, so here you go. No, here you go. Theta Brewster, let's do it differently, right? Theta Brewster plus 90 degrees plus theta of refraction is equal to what? 180 degrees. And here you go, the condition. You go get this one out of here, becomes 90 degrees. That's the condition. Okay, we cannot prove that mathematically at this level, at this course level, we cannot prove this condition. Only at a more advanced, only at a more advanced level, okay? So for this reason, you have to memorize this relation. Now, how do we find the theta Brewster? Okay, we go ahead and use the theta of incidence, right? We go ahead and use the Snell's law. How can you find the theta Brewster in terms of the index of refraction, right? We're using Snell's law right here. You go like that. In one, sine of theta 1, right? So when theta 1 is equal to theta Brewster, we are going to have a refracted angle of refraction. And then there is a relationship, right? Let's eliminate theta of refraction. We have to write down the theta of refraction in terms of the theta Brewster. Substituting that right in here. Right, what do we get? 90 degrees minus theta Brewster is going to be cosine of theta Brewster. And we end up having this relation here, N2 over N1. That's what we have there in the book, right? Yeah. Take the inverse, right? That's the theta Brewster. And it's a law, right? Not exactly a law, it's a consequence of Snell's law, which is a consequence of the least time postulate, or the least time principle. Okay, this guy found this so-called relation experimentally back in 1812. Okay, and now we can apply this relationship for different materials. Okay, so here you go. Light is incident from its example, real life example, right? Light is incident from air into a block of glass of n equal to 1.5. Find the angle of incidence for which the reflected light is polarized. Numerical example, right? Polarized, right? Solution. Solution. Apply the straightforward application of an equation, right? Go. N2 is 1.5. N1 is 1. You go. Take the inverse of this relation. And we can do that using my favorite software. Let's do that. Like mass. Have it. Here you go. Like mass. And you can do that for water as well, right? And so on. And many other indices of refraction. Here you go. Tangent of theta Brewster equal to 1.5. Take the inverse of that. Clarify, calculate. Here you go. That's radians. Don't forget that's radians, right? Now, if you want to know that in degrees, you multiply by 360 and you divide by 2 pi. Calculate. I'm getting 56 degrees. Okay, 56. If you come up with an angle of incidence of 56 degrees, the reflected light is going to be polarized. If you have, instead of a glass, a piece of glass, you have water, it's going to be, let's see, it's going to be different, right? Water is 53 degrees, right? Now, what about diamond? Diamond is what, 2.5, right? Index of refraction of diamond. Let's see if it's 2.5. Is it either 2 or 2.5? Let me check. It's 68 degrees. Let me see here. I did a little table before, right? Yeah, diamonds are around 2.5, 2.419. Okay, so let's copy and paste this one here. We're gonna make a table for theta Brewster. Okay, I'm pasting the wrong place. Go 1.5. We're gonna add another column in there. And you go. So let's start. Well, it doesn't matter. Vacuum to vacuum, right? You go vacuum to vacuum, what you get? Let's see here. Suppose that N1 is just for the sake of doing this math, 45 degrees? Huh? Yeah, you cannot have something like that, right? It has to be different interface. You have to have a refraction in there. So what about to air, vacuum to air, 1.00029. So light coming from space incident on the atmosphere. Okay, so what do we get? Should be around 45 as well, right? You know, the refractive index difference is very small. So here go 45, not applicable here, it's not applicable. But here should be 45 degrees because there is a difference in refractive index. Water, did we do for water? Let's do for water, 1.333, 1.333, here go. Oh, 1.3333, right? Here go. How much? 53 degrees. 53, 123, right? 53.123. Yeah. We do for glass. We did for glass, right? I forgot the result. What's the result for glass? 56. 56. 5631. And what about diamond? 2.419. That's a nice experiment that you can make. You go ahead, get a diamond, right? You get light incident at a specific angle, and you get 67.54. You go. Those are different materials here. The higher, notice that the higher the refractive index, the steeper is must be the angle of incidence. Okay. Remember polarization. Another way to polarize if light is incident in a direction parallel. In a direction parallel to the interface of the two media, to the interface of the two dielectric media. Angle is satisfied according to the equation. Right? So here we go. Okay, so this guy here is 90 minus theta Brewster, right? Theta Brewster plus 90 degrees plus theta of refraction is equal to 180. That's the best way to see that. So we're done with this chapter. And Let's see if we have any questions here. And let's go to our syllabus. We're still doing 33 here, 33 and 34 in Emma. A little bit behind. Okay, the 34 is going to be kind of straightforward. It's a nice material as well. Lots of simple practical applications. We can see this type of phenomenon in our day-to-day life rather easily. We are going to have lecture, right? The 2 o'clock, 9:58 right now. Let's go for the next chapter. We go to next chapter, images. Okay. Okay. And that's relativity, and then I usually do polarization after images. It goes according to the book. Different books organize it differently. Okay, that's what you're going to do now. Right here. Okay. Nine, 10 o'clock right now. Let's see. 10, 15, 11, 16. Yeah, let's do chapter 34 now. Okay, let's summarize here. Summarize. 2 special angles. Okay. The critical angle. Critical angle is an angle above which we have total internal reflection. Yeah. Brewster angle. An angle, not above, but at which reflected light is polarized parallel to the electric interfaces. Okay, so don't mix up one with the other. Critical angle and Brewster angle. Okay, both are angles of incidence. 2 special angles of incidence, right? Now, chapter 34. Chapter 34. They're doing just plane mirrors here. Looks like they're doing just plane mirrors. Yeah, they're doing just plane mirrors. Okay, okay, not just plane mirrors, also concave mirrors. Okay, image, formation of image. Spherical mirrors and lenses. Okay, that let's name like that, mirrors and lenses. Chapter 34, images. Image formation by mirrors and lenses. That's what this chapter is all about. So we exam 2, right? It's going to be on Thursday. Don't forget that. And in this chapter, we use the laws of reflection and the law of reflection. And it's now law. We apply, let's see, no, not we use, but we apply the law of reflection. Is now law predict image formation. Remember, this is geometrical because this is geometrical optics. As the name implies, we use geometry to predict the formation of an image. Okay? Predict image formation. We start with a plane mirror. Okay, so there's some nice techniques that we use to predict the formation of an image. Okay, so here you go. I'm going to start, step by step here. We start with a mirror. Okay. And then we position a source in front of the mirror. We're going to just play, source in front of a mirror. If you want to find out how the image of the sources is located, what we have to do, we have to use those laws that we learned before. Laws of refraction. In this case, it would be the law of reflection only, because this is what we are using here is a mirror. Okay, so here we go. We start drawing our light rays using what we know about light rays. Here you go. I'm drawing this first light ray. Angle of coming from the source, incident in the mirror, angle of incidence is equal to angle of reflection, right? Going another step, we can draw another light ray being incident in the mirror, on the mirror surface. Angle of incidence is equal to angle of reflection. Here you go. Here you go. That's another light ray. Another light ray. Let's see, this one here. I'm going to use this one here. Oops, nope, not here. I'm going to change colors, right? So it becomes easier. You go another light ray. Is this one that you see right here. I'm going to take this one out, otherwise it becomes too crowded. What you see right in here is the normal to the surface, the planar surface. If you want to know where the image is formed of this object, all you need to do is to extend the light ray. the reflected light ray. Not only this one, but this one as well. The point where those two light rays intersect is the point where the image of the source is formed. Right here. If you put more light rays there, you should get the same point of intersection. Simple enough? This technique works very well. Whether it's for planar mirrors, whether it's for spherical mirrors. Okay. If you want to come up with another light ray, I'm gonna make it. Here we go. Angle of incidence should be equal to the angle of reflection. I'm gonna put that in a different color. Okay. And let's see here. Let's see. I'm going to format face. Okay. I'm going to rotate. I'm gonna rotate. Yeah, it looks like I have to do in the. Let's see. Rotate, rotate, rotate. This angle is approximately 34 degrees. So it should go 68 to get the right, angle of reflection equal to angle of incidence. Okay, so if let's change the direction of this light ray. Okay, if I did everything right for all the three rays, they should all intercept at the same spot. Yeah, I did a good job, right? Here you go. See that? They're all intercepting at the same spot. Simple enough? Okay, so here you go. Let's play the movie, right? Mirror, source, first light ray, angle of incidence is equal to the angle of reflection. Second light ray, I don't want that. It's too close. Okay, second light ray, the red light ray. Angle of incidence is equal to the angle of reflection. And too much information yet, right? And right now. So here you go. Angle of incidence is equal to the angle of reflection. I don't need that yet. Extend the reflected rays. The point of intersection tells you where the image is formed. I'm going to label it as I. You need at least two light rays to find that out. Okay, where the image is formed. If you come up with a third light ray, the intersection of the third light ray should be the same at the same point. Image, I for image. That's the, and you can have a bunch of other light rays, right? They should all intersect at the same spot. Okay, I did that here. I don't need that. Let's erase those. Go, erase this one, erase this one. Okay, if you have an object that's standing up right in there, we usually choose those two light rays coming from the tip here of this object, reflected, extended, right? Here you go, and extended. This lower part of the object, we also have a light ray going here, right? And you should intercept at this spot. So here's the object, here's the image being formed. this distance here. Let me see what the notation that the book uses. Depending on the book, yeah, he used P and I. Okay. P is the position of the object, I is the position of the image. Did I use that? Oh, no, I used the Q. There you go. Depending on the book, they use P and Q. For this specific case, I is equal to P because it's a planar mirror. Okay. Spherical mirrors, let's see here. Here you go, same thing that I did, same idea, P and I. Okay. This type of image that you see right in here is called a, virtual image. Images. Okay, the let an object be placed at a distance P from the surface of a planar mirror. There will be an image formed behind the mirror at a distance I equal to P. And that can be proven, okay? How do we prove that? How do we prove that the distance is the same? This is just to do similar triangles, okay? This angle here is equal to this angle, okay? This length, notice that those two sides are parallel. Consequently, the height of this image is equal to the height of this object. For this reason, this distance here must be equal to this distance. That's why it's called geometrical optics. Okay. What about if we use a spherical mirror? Okay. In addition to planar mirrors, we also have spherical mirrors. The spherical mirror can be either concave or convex. Okay, let's start with concave mirrors. Concave mirror. Concave mirrors. Here you go. How the concave mirror is formed? The concave mirror is formed by generating a sphere and slicing a section of the sphere. The curvature of this hub, right, is just like a hubcap in your car, has a section, has a spherical section right in here. It's easier to make spherical mirrors. It's not the ideal case, but it's still a useful one because it's easier to make. Okay. This spherical mirror has a radius of curvature equal to r. Okay, and that's the section of a sphere. Any questions so far? So you go concave mirrors. Then I'm gonna work with convex mirrors as well. Okay. 33. Let's have a break, before we start this material in detail. It's 10, 15, 16 right now. Let's have another 15. Let's have another 15-minute break. Till 10:32, right? And then we go for 1 hour until 11:30. Take our half an hour break and come back for for more lecture. Any questions so far? I think this material is very nice because it's rather easy to understand. It uses just basic mathematical concepts, that is geometry, something that one of the first things that we learn in math, right? Okay, so let's take a little break now until 10:32, and I see you soon. I'll pause the recording, record it, share the screen, and concave mirrors, right? So how do we use those ideas of reflection that we learned before, right? Go here you go. First, we start, spherical mirrors. That's the easiest one to manufacture and the easiest one to visualize. How we visualize a spherical mirror? We visualize a spherical mirror as a section of a sphere. Okay, we usually, here's an exaggeration of a spherical mirror. Okay, real life spherical mirrors has a much smaller section than that. It's so small that we can hardly see a curvature in the surface. I have built one of those. Okay, but here I'm exaggerating how a spherical mirror looks like. You manufacture something that has this spherical configuration, and you illuminize the surface of the mirror, and you go ahead and play with it. We have spherical mirrors out there that can be bought at a drugstore, right? So here goes. So here go. Let's start with the sphere here. Sphere of radius r, right? We go ahead cut a section of this sphere, and after cutting, we illuminize the surface, preferably the surface, but in practice, what we do, the upper surface, right? The correct way to illuminize the surface of the mirror is to illuminize the top surface of the mirror. But for practical purpose, don't forget those mirrors, they always have a thickness, right? But for practical purposes, what do? They illuminize the back of the mirror. Why they do that? They illuminize the back of the mirror to protect it against corrosion from the air, okay? That's what they do in practice. And now we have this surface, this section of the spherical surface of radius r. Here's the center of curvature of the mirror. That's how we drew it. The center of curvature is the same one as this one here. Okay, let me copy it here, and it's supposed to be located in the same spot. Yeah, it is located in the same spot. Okay, as the other one. And if we shine light through the center of curvature of the mirror, we don't need, that's right. The light is going to be reflected back. Why is that? Because this direction here is going to be perpendicular, is going to be normal to the tangent of the surface of the mirror. Okay? Light passing through the center of curvature of the mirror is going to be reflected back towards the center of curvature of the mirror. You have to know that. That's an easy one to know. So here you go. That's how we represent a spherical concave mirror. We represent, as a flat, to make things simpler, right? Represented as a flat surface with those two lines describing a concave mirror. These hatches that you see here represent that the surface is reflective surface. In order to find out how images form in a mirror, right? We start like that. We draw the mirror in this way. Then we draw the axis of the mirror. Plus its center. Here you go. Mirror. That's too much. Mirror axis of the mirror and its center of curvature. Okay. Now, what else you have to know? Light going through the center of the mirror, passing through the center of curvature of the mirror, reflects back on itself, right? But what about light parallel to the axis of the mirror? That's another piece of information that you have to know. Another piece of information you have to know is that light passing parallel to the axis of the mirror is reflected towards a point that's midway the center of curvature. Makes sense? Here you go. D, assuming that D is much greater than CC prime, which is the curvature of the mirror, then this light ray will intersect a point here that has the center of curvature. Okay. So let's document that. Here you go. Physics note: concave mirrors. Concave. I'm gonna specify here concave spherical mirrors. Spherical mirrors are formed by cutting a section of a sphere. The resulting surface is a section of a sphere. This sphere has a radius r. Radius r and a center of curvature that we call point C for center of curvature. C for center of curvature, right? Light passing through the center of curvature is reflected on itself. Light parallel, light incident towards the mirror, right? Incident towards the mirror and passing through the center of curvature is reflected on itself. Light parallel to the axis of the mirror, the axis mirror is reflected back and intersects the axis at a distance equal to half the radius of curvature of the mirror. You have to know that. Half the radius. If the diameter, but there is this, you know, if the diameter of the mirror is much less than the radius of curvature of the mirror. That's the condition, okay? It's not that it happens for every light ray. Light parallel to the axis of the mirror is reflected back and intersects the axis at a distance equal to r divided by 2. Okay. This point of intersection is called the focal point of the mirror. Okay. We say that the focal distance is r divided by 2. With a focal distance, focal point capital F of the mirror with a focal distance F equal to r divided by 2. Okay, so here we go. Let's see if I have this drawing here. Here you go. Here's the focal point F. Did I this distance here? I'm going to illustrate this distance. Focal point. Don't forget here you go. Distance right in here. Let's put it this way. Right, here you go. Distance F, lowercase f, is equal to r divided by 2. Similarly, this other distance here is equal to r. Let's see here, which is the radius of curvature of the mirror. Okay. Path of light rays. Okay, how do I find that out? How do I find this distance here? Just by using the law of reflection, right? Angle of incidence is equal to angle of reflection. It's possible to prove that for diameters much less than 1. F is equal to r over 2 for diameter of the mirror much less than the radius of the mirror. Like that. That's two path rays. Okay. So far we have two path rays. No, one passing through the center of curvature and reflecting back through C, the center of curvature C, and reflecting back through C. And we have the second ray, second path of the ray, a second one parallel to the axis of the mirror, which reflects back towards a point F, the focal point, which is located at the distance of the center of curvature. You know, focal distance are divided by 2. By having those two, the path of those 2 light rays alone, we could, in principle, you know, find the location of any image that we want. But we usually use three light rays. Okay, so let's write that down here. The path of these 2 light rays are enough to locate the position of the image of the object, of an object being formed by this mirror. Just like we did for the planar mirror, just like we did for the planar mirror. Do you remember that? But we usually use a third light ray as a backup, you know, as a backup in case it is difficult to draw either of the light rays of either of the above light rays. Okay, how do we? Okay, the third light ray we draw is incident at the center of the mirror. Okay, so here we go. Let's go there. Light rays parallel to the axis converge towards the focal point, right? Here you go. Here's another light ray. Light ray passing through the focal point and the parallel. So here you go. Third light ray we draw, not incident at the center of the mirror, but the third light ray we draw passes through the focal point, capital F, and is reflected parallel to the axis. So it is the opposite of light ray 2, right? Light ray 1 pass through the center, light ray 2 parallel to the axis, light ray 3 pass through the focal point. But we can have a fourth light ray as well, but those 3 are the easiest one. Okay, here you go. Here's the 4th light ray, the one that I keep in mind. Those 4 light rays, we'll be using them. Okay, so there are a total of 4 light rays. A 4th light ray is the one that is incident at the center of the mirror and reflected at an angle equal the angle of incidence. Okay, so a total of 4. So a total of 4 light rays, or different light rays. You can use any combination of 2 of those 4 light rays to locate the image. Okay, here we go. A third light ray that passes through the focal point F and is reflected parallel to the axis of the mirror. And a fourth light ray incident at the center of the mirror and reflected at an angle equal to the angle of incidence, equal to the angle of incidence. Use any of these, use any two of these 4 light rays to locate the position of the image formed. Okay. Only 4, huh? It's not like 10, 300. Although you can come up with 10, 300, but those 4 are the easiest one to work with, the easiest one to draw. Okay, so here you go. Now here you go. Here's an example of image formation using geometrical optics. So again, we start with a mirror. Start with a mirror. In the next step, we illustrate the axis of the mirror. Okay. Next, what do we do next? We locate the center of curvature of the mirror. Next, step by step, we locate the focal point of the mirror. Focal point of half of the distance. Right? Let's see if it's half. It's actually, it looks like a little bit to the left, right? I like to do everything in scale so you can get a good, yeah, it's good, right? No problem, yeah, half the distance. Focal point. And then we position the object at a given distance from the mirror. Here you go, object. This distance we call the distance P. Procedure, right? To locate the image of a mirror. Go. Here you go. Move a little bit to the right. Distance lowercase p. Okay, so let's play the movie again. Here you go. When you're solving a problem, what do? You draw the concave mirror, draw the axis of the mirror perpendicular to the surface of the mirror. You draw the center of curvature and the focal point. You already know the focal point is half the distance to the center of curvature. You locate your object at a distance P. Oh, distance P from the mirror, not from the focal point. Here you go. Distance P from the mirror. Okay. And then what you do next, you want to find the image formed by this object. You can draw the light rays, a combination of 2 of the 4 light rays, right? We usually start with this one that goes through the center of curvature. Hey, wait a minute, something wrong here. Huh. Did I copy the wrong one? Okay, I copied the wrong one, right? Oops. Here you go. Yeah, I copied the wrong one. Light that passes through the center of curvature is reflected back, right? Towards the center of curvature. You go. That's the first light ray. The second light ray is light that's parallel to the axis of the mirror. You go. Reflects through the focal point. See the intersection point here? We can start to form to find out where the image is located. It's already here, but let's go another step, right? You need only, like I said, you need only 2 light rays, but you might want to practice with the other 4 light rays. So the other light ray passes through the focal point. Ooh. Uh-oh. Huh. Okay, I see. Okay. Pass through the focal point and reflects parallel to the axis. You can see that the third light ray coincides with the intersection of the other 2, right? And finally, the fourth light ray is the one that's incident at the center of the mirror. And if I do everything right and it's reflected back, let's do different colors, right? So you don't get, I'm going to do a little bit thicker. Here you go. The red one is going to be a little bit thicker as well. Thicker. I don't want this. Oh gosh, I don't want this F over superimpose there. Here you go. I'm going to put it here. Have enough space there, right? The third ray. Here you go. The third ray that passed through the focal point. I'm going to put a different color and thicker. Okay, and the fourth light ray. Now the drawing starts to become too busy, right? Which color I'm going to put? I'm going to put green color. Make it thicker as well. Okay, here you go. Reflect back, and if I do everything right, it should intersect the same spot as the other ones. This angle here is equal to this angle. So practice that in your paper, right? I'm going to, let's see, play the movie again, right? Mirror, axis, center of curvature, focal point, object, distance of the object to the mirror is P, right? First light ray through the center of curvature, second light ray parallel to the axis, third light ray passing through the focal point, fourth light ray towards the center of the mirror. Let's get this guy a little bit thicker. Okay. And I'm gonna bring down this P. You go. And now I'm gonna simplify this drawing. I'm gonna just show the light rays at the point of intersection, okay? I don't need that anymore. I wanna make it simpler. I don't need this incident light ray. I'm gonna shorten this reflected light ray. I will keep my center of curvature. I don't need this incident light ray. I don't need this incident light ray. All right. They are all supposed to intercept at the same point. You can do that in a millimetric paper and practice. So you can memorize it more easily. Okay, the resulting is an image, an upside down image. Oh man, this guy is too big. Let me get it smaller. Yeah, can be a little bit big. Okay, good. I like this size. And this one is going to be my image, denoted by letter I, capital letter I. We can zoom in, right? So you can see it more clearly. Let's make it a little bit shorter. Can I get it shorter? Yeah, I got it shorter. That's the image. And this distance. And the distance of the image, this image is upside down, you can see it. You go, this distance here, your book called little lowercase I. Okay. And now I'm going to simplify that image even further. Eliminate, oh, what's going on here? Oh, I see. Let me. Here we go. I'm going to simplify this image even further by eliminating the light rays. Okay, and that's what we get. That is a straightforward relationship between I and P. Okay, there is a straightforward relationship between I and P. like I said, this geometry, you can use similar triangles to find that out. Okay, I have here in my notes, I derived that here in my notes. I'm not going to derive it here because it takes some time. But the equation, the final equation, is very easy to memorize. Okay. Let's see. The equation is the following. I don't have the equation here, but anyway, let me write down the equation here for you. Any two of these 4 light rays, okay? The position of the image can be calculated using, can be derived using similar triangles, using geometry. Triangles, and the position of the image in terms of F and P can be derived using geometry. Similar triangles, and that's going to be given by the following equation: 1 over F equal to 1 over P plus 1 over I. Simple enough. Okay. Let's look at the book here. Here you go. Okay. Here, he's doing, okay, this planar mirror, concave mirror, you know, convex mirror. Here you go, parallel light rays, right? He's doing the concave mirror, convex mirror together with the concave. We're going to do the convex mirror very soon. Okay, here he's doing some other light rays that we don't use, okay? Usually don't use those light rays. Okay, what else? What else can you, I can tell you, okay? I'm gonna call one more slide. I'm call the height of this object H. H. 90 degrees. I'm gonna put this guy 90 degrees. Here you go. Doing good. Ah, didn't do it. Ah, no, it's transparency. I don't want transparency. Okay, I want to rotate it. Size and position. Rotation 90 degrees. Good. So if I did everything right, here you go. That's H. And we can do the same thing for the image. That I call, here you go, H prime. prime, and I need another, double arrow here. Right, H prime. There is a relationship between them as well. Here you go. H prime over H is the magnitude of the magnification of the object. It can be derived from the magnification of the magnification of the obtained as being H prime divided by H, which is also related I divided by P with a negative sign. Okay. Magnification, okay? If I and P are positive, then the magnification is negative, which means that the object is upside down. 1115 here. This relationship here that you see applies both to concave mirrors and convex mirrors, okay? Let's do some special cases, okay? Let's work some special cases. Special cases. There you go. P is example. P equal to R. Find I. Solution. Okay. P equal to R. Right? The object's placed at the center of curvature. We do know that the focal point is half the radius of curvature. We end up with this equation here. Okay. We can pass the inverse of the radius of curvature to the left side. And when we do that, when you do that, we get 1 over R, right? And look what we get. We get this equation here that implies that the image is formed at the same position of the object. With one important difference. What's the difference? The difference is that the image is inverted. Okay, here you go. Because the object is imaged at the same position, it's not magnified, right? The size of the image is going to be equal to the size of the object, but with the upside down image. So let's do that. Here you go. I'm gonna show you exactly what it means if we put this object right here at the center of curvature. The image formed. It's formed. Is that I'm gonna just copy this one and invert it. Yeah, here you go. Inverted. I'm gonna put it like a dashed, so you know it's the image. Let's see this one here. Yeah, better, right? Center of curvature. That's my P, which by the way is equal to Q in this specific case. Okay. Oh, not Q, but I. Magnification is 1. I don't need this H prime anymore. You go. I don't need that. What about, let's see, we have 10 more minutes to go before our break, right? Another example. Go. P equal to F. Find I, right? Here you go. That's going to be F here. F is going to be 2 over R. Nope, that's 2 over R. Right? And now here you go. We have this part of the equation equal to this part of the equation. Right? And then here you go. What we get? We get 0. Right? 1 divided by the image is 0. 1 divided by the position of the image is 0, which implies what? Which implies that the image is being formed at an infinite. This means the image is being formed at a infinitely long distance. We call it improper image. We can do the math for that as well. We can do the drawing for that as well. Let's let's go. Let's see here how I'm gonna do that. I'm gonna do like that. I'm gonna use this drawing here. I'm gonna put this object at this spot. Okay. So here you go. Light rays parallel to the axis, passes through the focal point. Light ray. Oh, here you go. In this case, we do something like that. Light rays that pass through the center of curvature, okay, is reflected back towards the center of curvature. See that? And if I do everything right, here you go. I gotta put it here. Note, see that my edge of the mirror is a little bit off, right? So I have to increase the size of the mirror so we make sure that the light ray is incident on the surface of the mirror. What else can we do? Okay, light ray passing through the focal point, right? Oh, this one we cannot do it. We leave this way. We don't need that, right? What about this one? We don't need that. So let's see, we have two light rays. We can come up with another light ray as well. The green one. Here you go. Center of the mirror. Oh. Here you go. And what do we get? Well, if you do everything right, we're going to get parallel rays here that never intersect each other. Okay? And we can even prove that. That's why we say they never intersect each other. So we say that the image is formed at infinitely long distance. Those rays, those light rays, they never converge to one another. Okay? That's what that example means. 1125. Any questions? I took attendance, right? One more example. Let's see, focal point. Oh yeah, let's do it closer to the mirror. One more. Okay, now I'm gonna bring, and by the way, you know, there are some simulations, nice simulations. Instead of doing all this hard work here, you can also look at some simulations out there in the internet. Let's go for that. Image formation by mirrors. Simulation, right? There's a bunch of information for by concave mirror simulation. Here you go. There's a bunch. Let's try this one here. Concave and convex mirrors, old physics. Let's see if it's a good one. Oh yeah, I like that. Okay. Here is the object. Can I slide it? Oh no, I cannot slide it. What a shame. Okay, this one is not a good one. Let me look at another one. Concave mirror, refraction mirrors, simulation. Let's see. Optics bench. Let's see. That doesn't look like it's. And by the way, what we do here is exactly what happened in real life again. Okay, image formation interactive to this physics simulator. Maybe this one here. Let's see, object. Oh, he doesn't let me move. Download. Maybe I can have to download it. Yeah, I cannot move those things. No. Yeah, it used to be so easy to find those. This to study reflection simulation. Let's see, online lab. Come on, man. Bear with me. We have two more minutes to do that. Wow, it's taking forever. Okay, I'm getting impatient here. Let's try another one. Simulate analysis of this. Oh, let's try this one here. Can I? That's the focus object. God, how do I get this thing to move? What a shame. Maybe I have to change it here. Distance of the object is 10. Huh. Doesn't let me change. Oh gosh, that's so frustrating. Let's try this one. Okay. Okay, this one. Okay, this one works. Good, here you go. The spherical mirror. See that? Light rays parallel to the axis. Subscription. Oh no, they didn't use to charge me that. Oh gosh. Yeah, elementary school, secondary school. Oh gosh. Let's see if he let me. Okay, passing through the center of curvature, reflecting back parallel to the axis, reflects through the focus. And he didn't do the third and the fourth light rays, right? So I think he's gonna charge me to do that. What about fat? Maybe fat we can do is fat. Concave, physics, ego, reflection, ego. Huh. Download. Okay, so let's see. Huh. Something wrong here. Simulations, let's try it here. All seems. Fat used to be different. Let's see. Okay, light and radiation. Must be light and radiation. You go geometric optics right in here. Lens mirror. Here you go. Okay, good. So here you go. Here you go. Here's the image being formed, right? So here you go. They see that they have the light ray that's incident at the center of the mirror, but they don't have those light rays that I used. What a shame. Yeah. This should be the radius of curvature. Let's see, let's increase the radius. Yeah, see, this is the radius of curvature. They don't have the parallel light rays. They don't have the light ray that goes through the center. They don't have through the center of curvature. They don't have the light ray that goes through the focal point, okay? But they do have that light ray that reflected from the center of the mirror. Well, if you find a simulation, let me know. I'm not being, I'm not being lucky here. Those simulations, they used to be easier to find. Concave mirror physics. Let's try this one. Launch interactive. Let's see. Using interactive. Okay. Loading. Concave mirror image formation. Okay, here you go. Yeah, this is a different one. Watch out, right? But they don't hold the light parallel to the axis, reflects through the focal point. Light that passes through the focal point reflects parallel to the axis, right? And the image is formed right in here at this spot. Can I move this guy? It doesn't let me move it. Draw all rays. Now it's too much, right? It's too much. Click start. Wait, browser. I don't think yeah, unfortunately, yeah. Looks like they start to analyze it. Looks like they started to make life difficult to find those simulations. But we used to have a bunch of those out there. And the mirror lab, let's try this one. Let's go another 2 minutes here. Let's see, that's the length, right? Oh, you gotta launch it first. Drag me. Yeah. But I want, okay, good. Looks like I finally found one. I don't want a lens, I want a mirror. That's the object, okay? Here you go. When the object is very far away, can we move this mirror? We cannot move this mirror. When this object is very far away, we have an image that's forming closer and closer to the focal point, okay? As we keep approaching the object towards the mirror, okay, so here you go, light rays parallel to the axis, reflecting through the focal point. Light rays at the center of the mirror, incident at the center of the mirror, reflects at the same angle, focal point parallel. He didn't get the light ray passing through the center of curvature, okay? So watch what happens to the image, right? As the object goes further away, the image gets closer and closer to the focal point. As the object moves closer and closer to the focal point, the image moves further and further away from the mirror. At the center of curvature, the image and the object are in the same position. Okay, as we move closer towards the focal point, the image moves further away as well. Not only moves further away, but now the image becomes larger than the object itself. Okay, as we reach the point here where we have the object exactly at the focal point, the light rays are reflected parallel to each other and the image becomes improper. Okay, see, the image is to the left, and then as you move closer and closer, okay, notice that the image is no longer being formed to the left of the object because those light rays become divergent. However, we do get an image behind the mirror. That's the type of image that we call virtual image. Okay, so here you go, a virtual image being formed behind the mirror. Image formed in front of the mirror are real image because you can project them into a paper. Images formed behind the mirror are virtual. That's what we have here is 1135, 1136. I will review that when we come back. Okay, it's we're gonna have a break for half an hour. Break till 12:06 p.m. Any questions before you go for the break? I'm gonna post result. Good. So what we're doing here, I'm walking you through how to look at your grade there in this file. Okay, so here you go. When I corrected your lab report, I generate that HTML. When I correct, this correction that you see here is the correction for your spreadsheet, okay? When I correct your lab report, I generate a folder and an HTML file. Okay, so let's go there. Here you go. Upload it. So I corrected the spreadsheet of your lab report 1 and uploaded it to your group folder. Okay. So what you have to know about it? What do you have to know about it? One, first, go to your group folder. Go to your group folder. 2, look for P39L01 group number, whatever, let's see. Group number underscore files. This is a folder. And P39, P39L01 group number .html file. The HTML file, okay? Special format. You cannot open that from inside your, just look for them. Download both files, both the HTML file and the folder. Okay? Download to your hard drive. For the HTML file and the folder. Okay. So how you do it? You cannot open that from inside the Google Drive. Okay, so here you go. Highlight both of them, right? Right click and download. That's what you have to do. Okay. So how do you do that? I'm gonna document again. Highlight both the folder and the HTML file. Right click it and download. Download it. Okay, that's what you have to do. Okay, it's finished downloading here. Are you doing that? But for everybody who wasn't my student before, okay? So let me go through you folks. Elena, are you following, Elena?
Yes.
Okay, good. What about Zachary? Is he back?
Yeah, I'm back.
Okay, good. Are you following Zachary?
Yes.
Okay, what about Daniel and David?
Yeah, Professor, I'm back.
Okay, good. So highlight Crystal, right? Let me take attendance in this meantime, right? Since we're doing that, I'll take attendance as well. So Toby, are you there?
I'm here.
Okay, good. You know how to do that, right, Toby?
Yeah.
Okay, good. Pedro Flores, do you know how to do that? Pedro, do you know how to look at your correction there? Pedro sent me a message earlier on. Now he's not answering. Are you there, Pedro?
He sent a message in the chat.
Yeah, I know. Yeah, but it looks like you walked out from the computer. Lawrence, are you still there?
Yeah, I'm here, Prof.
Okay, you know how to open those files, right?
Yes.
Good. Kenny
Thank you.
Villagomez.
Yes, Professor, I got it.
Okay, you know, right? Nolan Williams. Yeah, good. Harun, you also know how to open those files, right?
Yeah.
And Musa. Okay. Daniel, are you there?
Yes, Professor.
Okay, you're following, right? And Dave, are you there? Okay, good. Zachary, I heard from you, right?
Yeah, I'm here.
Okay, and Elena. Okay, so here you go. I'll get back to you all. So to the remaining of the students, let's do that together, and you have to make sure. Okay, now I have the file here downloaded. What I like to do, you know, it's zipped, just compressed, right, into a zip file. So what I like to do, I like to go show in the folder. It's usually go to my download folder. See, download folder, yeah. And what you have to do next, you have to unzip those two files that inside. In my computer, what do? I just highlight those two guys. I copy it. Here you go, the HTML file and the folder with files, right? With additional files. You have to take those two files. I like to copy because just cutting it sometimes doesn't work, okay? Go back to the previous folder, in the case my download folder, and paste them here. Now this folder and this file, they have been uncompressed, okay? Both the folder and the file, they must be in the same folder. Do not drag this guy to this folder here. Do not do that. Keep it, both the folder and the file in the same folder. Now I can erase it. I don't need this zip file anymore. I don't need that either. What is it doing here, right? Once you do that, you know, you double click this file, okay? Let's see. And then you'll be able to see what you got wrong, what you didn't get wrong, okay? So it's color coded. All this correction is color coded. I wrote a computer program to correct your spreadsheet. And I have been doing that for some time. It has been working pretty well, the system, and I grade your spreadsheets accordingly. Now, let's see here, one more student coming. Let's go through the attendance again. Now, let's see, Elaine, Daniel, were you able to open your file already?
No.
No? So let's see, download. First download, right? Did you download it?
I was just watching the video. I've not tried yet.
Yeah. Go ahead, download it. Download them. You're group number 2, right? I want you to learn how to do that.
All right.
Download it. Here you go. L01, right? Peter HTML file and the folder. P39 L01 folder, P39 L01 file. Right click them and download. Okay, download them first, and then so I will get back to you, Daniel. Not yet. What about Dave? Were you able to download it? To download your folder and file? Dave, let's see. Dave. Yeah, Dave is here, but it's not answering, right? Oh yeah, here you go. You answer me. Not yet. Oh, yeah, please download it. Zachary, were you able to download the file in the folder?
I'm working on it right now.
Working, okay. Working. Elena, were you able to download the file in the folder?
Yeah, I'm also working on it.
Oh, you're still working, okay. You didn't do that yet. Crystal? Is Crystal there? Let's see, Crystal. I don't see Crystal here. Okay, so Dave Myers, are you there, Dave? Okay, were you able to download the file and the folder? Yes, okay, good. Now the next question is, were you able to open the HTML file? You have to double click on the oh, wait a minute, before open, you have to uncompress, right? Unzip. Were you able to unzip both the file and the folder? Dave? Not yet? Okay, not yet. So unzip them, and how to unzip it again? You have to double click inside that zipped folder, copy the contents, and paste the contents outside the zipped folder. That's what you have to do. So let's document here. Download your hard drive, highlight both the folder, right click it and download it. Look for the downloaded. Okay, Upon downloading, the folder and HTML file are downloaded in a zip format. Zip format. They're downloaded in your tool. They are usually, depend on the computer, they're usually downloaded to your downloading folder, download folder. Depends on the computer, but in general, it goes to the download folder. Yeah, downloads folder in your hard drive. Okay. Locate the zip folder. Okay. It should be, let's do that again. I'm going to download groups, group 3, right? This one and this one. Download it again. It downloaded with a name. It takes some time. Okay, here you go. See, that's the name that it downloads it. Right in here. It's a big name here. .zip. So locate the downloaded zip folder in your computer. Download should be in downloads folder. Okay. Double click the zip folder. Okay. Double click the zip folder, and I'm going to do that again. Next, copy the contents inside your zip folder. Okay. Copy the contents. Select all copied contents. Paste contents outside the zip folder. Wait, what? I'm going to do that again. Here you go. I'm going to paste the contents. See, because the content has the same name, they're going to overwrite it. In this case, it have the same name. Okay. Now you should have the HTML file next to the P39 L01G group Y HTML file next to the P39 folder. Keep them separately. Keep them separately. Do not drag the HTML file into the folder. Do not do that. Once you have done that, click, double click, not click, double click the HTML file, and you will see the correction of your lab report and grade. Okay. Everything that is incorrect, color coded. The grades are at the bottom of the file. The grades and rubric at the bottom of the file. So let's see if you 13 steps here. Let's see if you manage to do that. Robert Faust, he should know how to do that, right, Robert? Are you there? Just tell me that you're there. Good, thank you. I'm gonna say that they already know how to do that. Daniel Freddy are you there? Daniel? Daniel, I don't see Daniel here in my list. Okay, so no attendance. Olivia Kroger, are you there, Olivia?
I'm here.
Okay, were you able, what were you able to do so far?
I could download the files, but I can't open them, so I'm still working on it.
Okay, so you got the zip folder somewhere in your computer and you are not able to open the zip folder? Is that what happened?
Yeah.
Okay. Well, I gotta figure out what's going on there. Maybe you don't have the software to unzip it. Is that possible that you don't have the software to unzip it?
Yeah, I don't really know what's going on, but when I try to open it, it says the file may have been moved or deleted.
Really?
Yeah.
Okay, so download it again. Maybe something happened in the process. Okay, delete what you downloaded before and download it again. You're group number 4, right? Let's see.
Yeah.
Let's try here, group number 4. Here you go, L01G4, right? HTML folder and file. I'm gonna download it. It takes some time to download. For some reason, Google Drive is very slow at downloading those zipped files. Here you go. Now I downloaded. Right in here. Click show in folder, right? Now let's see if I can go inside. Yeah, I can go inside. See that? Folder.
Yeah, I think I just have to try it again.
Yeah, download it again. Double click the zip folder. Copy. Either you did something wrong in the first trial, or maybe you didn't download it, the computer didn't download properly, or I suspect that maybe you don't have an unzip tool there, unzip app. Maybe that might be a possibility, but I'm not sure. Okay. So Olivia, right? I'm talking to Olivia. That's yes, but you're not able to unzip it. Check Lou. Were you able to download it, Chuck? So first is check there. Check. Not listed here. Okay, 0. Not present. Amalia. Are you there, Amalia?
I'm here, Professor. I was able to download the file and look at it.
Okay, so were you able to unzip it as well?
Yes, I was able to unzip the file.
Okay, did you copy and paste outside the zip folder?
Yes.
Okay, good. Okay, so that's the next step, right? Next step, paste files outside, paste outside, and then the next step is open HTML. Did you open the HTML file?
I opened the HTML file.
Okay, do you have any questions about this here grade there and all the correction that's inside?
No, I don't have any questions. Thank you, Professor.
No. Okay, but you see the grade and everything, right? The color code.
The grade and all the color coding and everything.
Okay, good. Good to know. Okay, so we have a case of a successful student. And Tiffany, are you there, Tiffany? Yes, okay. Did you download the files, the file in the folder? Oh, you're able to do everything. Good. Do you have any questions about the about the color code and the rubric there? Tiffany? Okay. Okay, let's go to Anthony. Yeah, Anthony, I was still working on unzipping. Okay, he downloaded, but it's still working on unzipping it. Unzipping is just a matter of, in my computer, it's just a matter of double click the zip folder, copy the content, and paste it outside the zip folder. It's just a matter of doing that, at least in my computer, right? Sha, are you there?
Yes, I'm here, Professor.
Okay, what is it supposed to be for table of first graph? Oh yes, I will walk you through that, Tiffany. I will walk you through that. Okay. Let me ask the other students, and we will get there. Okay, so you're able to download, right?
I downloaded it and I checked it, and I have a question about the confidence level because I think you took 1 point away from the.
Okay.
Yeah.
Okay, so let's if you can stay after hours would be better. Okay. After
Okay.
hours, during the office hours, and
Sure.
then let's see what's going on there.
Sure.
Okay, I some students, they were reporting the incorrect R-square, and because of the incorrect R-square, because they were using an incorrect R-square, they didn't get the right CL. Okay, that might be a possibility. That might be a possibility.
I will double check to see if we get the correct one or incorrect.
Okay.
Thank you, Professor.
So you did a zip, you paste, and you open. Good. You are able to see everything there. Daniel Liang. Yes, I have done all. Okay, good. No problem, right? Any questions, Daniel? Okay, let's go for Ryan. Are you there, Ryan? Ryan McNeil. Yes, you did everything. Okay. Any questions? No? Okay, good. Ryan already know how to do that, right? You were my student before. Claire? Are you there, Claire?
Yeah, I haven't been able to find the file actually.
Oh.
Is it just shared in our group folder?
Yeah.
Okay.
No, yeah. So you're group number 6, right? So let's do that together.
Yeah.
Let's do that together. Group number 6. You go. Go there in your group number 6. Highlight the folder for lab 1 and highlight the HTML file for lab 1. Do you do that?
Oh, okay, yeah, I see.
Okay. Next, right click, right? Download. Right click, highlight download. When you start download, it takes some time, see that? It takes some time for zipping the files. It's compressing those files, make it faster to download it. Eventually download, okay, download it. And then, oops, it should show up here. The download file folder. Oh, here you go. See? At least in my computer, it's like that.
Do I have to download them together at the same time?
No, you don't have to
can
download.
I just? Okay,
It can be separately. Can be separately. I prefer to download together at the same time, so you do everything the right way. Okay.
Okay.
Why it's taking too long to download it?
Yeah, it's taking a bit of time.
Yeah. Sometimes it's faster to just download them separately.
Okay.
This file goes very quickly, but that folder usually takes a long time. So that's why I'm downloading them all together, because since it's gonna take a long time to download the folder, a single file downloads pretty quickly. Okay.
Okay.
So once you download everything, you go, watch for this little window here, right? Show your folder, and when highlighted is the folder that you're looking for. Okay. So let's move to the next student. Try it a little bit there, and then if you have any problems, okay, you're working on the downloading, right, Claire? George,
yeah.
George Risk, are you there? Yes. Did you download the file, George? the files? Got everything? Okay. Were you able to open the HTML and see everything in there? Grades, color code, what you missed, what you didn't. Okay, good. So let's go for Jennifer now. Welcome. If you have any questions, let me know. Yes, I was able to do everything. I have a question, see all menu. You can go. Yeah, let's do that during office hours. Thank you. Thank you, Jennifer. 1, 2, 3, and 4. Okay. My memory recollection, Jennifer, is that I remember seeing some students who reported the wrong R square, and because they reported the wrong R square, they ended up reporting the incorrect CL. That's my memory that I have. The memory that I have when I was correcting that. Noah, are you there, Noah?
Yeah, I was able to do everything. Saw the grade and the color coding.
Okay. Do you have any questions?
No, just Jennifer's, but she already asked it.
Okay. Natalie? Got it all? Okay. Any questions, Natalie? No? Okay. Next, Mengshu. Yeah, everything works. Good. 1, 2, 3, 4. Good. Next, Nathan. Yeah, everything works. Nathan. So you did everything. Any questions, Nathan? No? Okay. Next, Sarina. Okay, were you able to download the file and folder? Sarina, good. Were you able to unzip them? Yes, you got it. And did you open? Were you able to see your grades there, everything? Yeah, okay, good. Any questions? Do you have any questions? Do you have any? No? Okay, good. Next, Alexis. Hold on, remember how to do it. Okay, good. 1, 2, 3, 4. Good. Next is Darnice. Are you there? Let's see. Yep, I have downloaded the zip file. Okay. And decompress it. I'm having trouble opening the HTML file. Okay. So the problem is, and you copy and paste it on the outside, right? The problem is okay. So let's see. Let me go through every student and let's see. Let's do it together. Then that's group number 8, right? Group number 8. Here you go. Open, right? Highlight. Okay, download. Take some time. That time okay, good. Download it. Here you go. Your folder is right in here. It's located on my download folder. See, download it right here, right? Highlight both. First, open the zip folder, go inside it, highlight everything that's inside there, copy, and paste it. Group 8. The next step is to double click this HTML file. Right? Did you get to this point, Dennis? Here's your folder, here's your file. Does it look like that? P39 L01GH. Make sure it looks just like that. The folder must be located in the same place that the HTML file is located. So I'm going to open your HTML file, but I'm going to stop sharing the screen because I do not want to disclose your grade to everybody else, okay? Let's see if everything is all right here on my side. Yeah, I can see it. I can see it. Everything is here. Yeah, I can open it. There's no problem. Here you go. Let's see, where is your, I'll try again. Okay, good. And anybody else? Yeah, Olive is not here. You're the last one here, right? So who is having a problem? Okay, so Darnis have a problem opening. Oh, okay, here you go. Now let's go back. Toby, Pedro, Lawrence, Kenny, Nolan, Aaron, right? Daniel, going back to you. Cycling back with you, Daniel. Don, were you able to download the file and folder, right?
Yes, sir.
Unzip it, paste
Yes,
it.
sir.
Were you able to open the HTML file and see your grades and everything?
Yes, sir.
Okay, good. Dave, what about Dave? Did you do everything too, Dave? You should be able to work with your brother, right? In case you have any problems. Are you working with Dave, Daniel?
Yeah, I think he's in the restroom, but yeah, we are working together.
Okay, good. What about Zachary? Let's see, Zachary, are you there, Zachary? Yeah, Zachary is not answering. Oh, okay, downloading. Okay. Oh, you mean the application or downloading the application? Downloading 7-zip. What do we mean downloading 7-zip? Are you installing the application in your computer or are you downloading the file and folder? Well, okay, so let's think about this question and get back to me, Zach. So Elena, are you still working there, Elena?
Yeah, I was able to open it.
Okay, good. It is still open. Okay, so you saw everything there, right, Elena?
Yes.
Okay, good. Do you have any questions?
No, I think I'm good.
Okay, let me document those students who need to ask questions, right? So let's see. No question here. Do you have any questions, Daniel? Daniel Magbo, do you have any questions, Daniel?
No, Professor.
No? Okay. Next, Crystal. Crystal, I don't think she's here, right? Yeah. No Crystal. Okay. Next, David Myers. How's your status there? How's your situation, Dave? Were you able to? You're done? Okay. Were you able to open your HTML file? Okay, did you see your grades, everything, right? Do you have any questions? Any questions? No? Okay, good. So let's go, Robert. Okay, Robert, do you have any questions, Robert? Robert Faust? No? Okay. Daniel Freire, how's your situation there? Did you unzip it? You paste? Cool. Daniel Freire, let's see here. Daniel Freire. It doesn't look like he's here. No? Oh yeah, he's 0 here. Okay, he's not here. Why did I put A? Okay, Olivia. Did he drop the class? Okay, thank you for letting me know. Okay, is you working on that? Okay, but did you download it, Olivia? You downloaded, right? And now the question is whether you downloading. Okay, so you're downloading the zip application, right? The zip app. Is that what you're telling me? Yeah. Okay. Sometimes those things come already in your computer, right? So Now let's see, Amalia. Amalia, you did everything. Do you have any questions, Amalia?
No, I don't have any questions, Professor.
Okay, Tiffany, do you have any questions? I asked it before about the units. Okay, yeah, okay. So let me put a Y here, and then we're gonna address that soon. Okay. Yeah, bear with me, and we can do that during your office hours. Okay, you can stay for the office hours. Anthony Lopez, how is your situation there, Anthony? Was able to open it. Okay, good. Any questions, Anthony? No. Okay. Shah, you had that question, right? That you want to address with me during the office hours. Is that right?
Yeah, but I figured it out, Professor.
You figured it out? So
Yeah.
what do I put? Y or N? What do I do here?
I'm done.
Okay.
No question. No questions.
No question. Okay, good.
So,
Daniel Liang.
do we have another lab today?
No, we're gonna just lecture. Okay.
Okay.
I'm just gonna lecture, cover the materials for the exam. Daniel Liang. So let's take a look at the syllabus, right? Yeah, here you go. Lecture. Hopefully we can finish chapter 34 today. I have just one more hour. No questions? Okay. Ryan McNeil, you don't have any questions, right, Ryan? Okay. Claire, were you able to do, to move forward?
Yeah, I was able to get it.
Okay, so you downloaded, you unzipped it, you opened as well, right?
Yeah.
You have any questions?
No, thank you.
Okay, George Risk. Let's see, George Risk. I don't see George here. He was here before, but I'm gonna put a question mark here. Jennifer, do you have any questions, Jennifer? Yes, you have questions. Okay, so you want to stay for office hours, right? Okay. Okay, Noah.
No questions, Professor.
No questions. Okay, Natalie Santiago. No questions. Meng Shu. Meng Shu. Are you there, Meng Shu? Okay, I'm gonna put a question mark here. Nathan. Do you have any questions, Nathan? Okay, I'm gonna put a question mark. No questions? No. No questions. Okay. Sarina, any questions, Sarina? No. Alexis, any questions? Alexis, let's see. Okay, I'm gonna put a question mark here on Alexis. What about Darnis? Do we have any questions, Darnis? Are you there? I was able to open the file. I have no question. Okay, good. Okay, so make sure review what went wrong in this lab report, and make sure that you don't repeat the mistakes, right? In the upcoming report.
Professor,
Yeah.
I sent a chat. I was able to open the file. I have no questions.
Okay.
If you could-
Okay, who is that?
Darnice Simon.
Yeah, you are breaking up a little bit. Okay. Yeah, so just review your, for everybody, right? Just review your what you didn't get it right, and I still didn't correct the lab report number 2. Okay, and if you want to use the information of this correction to fix your lab report number 2 and the other ones, that's fine with me. Okay, but I'll give you, let's say, I'll start correcting lab report number 2 tomorrow. So I'll give you, until I give you today to change lab report number 2 if you need to. Okay. So let's write that down here. Review the correction of report of lab 1, and feel free. Let's see. Make sure you don't make the same mistakes. Don't make the same mistakes in the other reports, right? Report, I did not correct report of lab 2 yet. So, but I will do that tomorrow, but I will do that tomorrow after class. So if you want, to change anything in the report of lab 2, you have it until tomorrow, let's say 2 p.m. Okay. Lab 2 or 3, right? Report for lab 2 or 3, based on what you learned from this correction. I was able to, okay, good. So let me save that here. And we can continue with the mirrors, right? Hopefully I'll be able to finish it. Let's see, we started at what? We started at 12. Let's have another break, right? Let's have another 15-minute break since it's almost 1 hour since we started. And then we can go until 2 p.m. To try to finish this chapter. Break till 1:11 p.m. Okay, so let me save it here, and I will see you in 15 minutes. All right, again. Start sharing the screen. Here you go. Okay, so let me try to do an animation here. Oh, wait a minute. We can go to that simulation, right? Instead of doing all that animation, maybe it's this one, right? No, it's not this one. Oh yeah, this one here. Okay. That's a very good way of understanding how this whole image formation works, okay? We can, come up with this movie. Let me turn off one of the rays. Okay, here you go. If I want, I can turn off rays, right? Otherwise it becomes too busy. They are displaying only rays 1, 2, and 3. You can, like I said, you can display rays, 4 rays, right? So what's missing here? Which ray is missing here? The ray that's missing is the one that goes through the center of curvature. That's the ray that's missing, okay? They have the ray 1 parallel to the axis and passing through the focus. They have this ray that passes through the focus and reflects parallel to the axis. And they have this third ray that's incident exactly at the center of the mirror and reflected at the same angle. Okay, yeah, it's kind of puzzling why they don't show this other array. It's really puzzling because it's a very reliable ray, works under every condition, whether it's an approximation or not. It's very puzzling, but let's keep it just 2 light rays here. That's all we need to form the image. The image is formed right in here. I need you to practice that by hand, pen and paper. Do your drawings on your own, right? So look what's happening. Okay, the further away your object is, the closer it is to the focal point. Actually, if the object is at a distance that is infinitely distant, the image is going to be formed as the focal point of the mirror. Okay, we can prove that according to the equations that you saw. You go right in here. Okay, at which point you go? Example, another example. At which position does the image of an infinitely distant object is formed from the mirror? Okay. Okay, solution. All you have to do is to use the equation that you're familiar with. Okay, here you go. We want to know the position of the image. We also know that the object is very far away from the mirror. Very far away from the mirror means what? Means that P is much greater than the focal distance. Okay, that's what it means. If P is much greater than focal distance, then what you see here can be approximated to something simpler. You know, it can be approximated to 1 divided by, you know, a very large number. I'm going to put it here infinity, right? And 1 divided by a very large number is 0. It's close to 0. And now we end up with this simpler relation. Okay, here you go. I'll get 1 divided by the focal point is approximately equal to 1 divided by I. What does it mean? It means that the image is formed near the focal point. And that's what that drawing or that simulation is trying to tell you. We cannot, let me see if I can, I cannot move my object further to the left, right? Nor the mirror further to the right. But I can do the following. I can decrease the size of the focus, okay? And you can see that the image is going closer and closer to the focal point. Okay, let me turn off the rays. And not only the image is getting closer and closer to the focal point, but the image also is getting smaller and smaller. Okay, make sense? Okay, let's increase the height. Here you go. You increase the height, the size of the image also increases. Okay, I decrease the focal point, the focal distance, and the image gets closer and closer to the focal point. Make sense? Let's go turn on those light rays again. And let's play the movie again. Here you go. I can do that with my drawings there in the PowerPoint, right? But it's easier to do that here. Here you go. As I get closer and closer, the object gets closer and closer to the mirror. See where the reflection is taking place? The reflection is taking place right here at this line. Okay, and not at the surface. It does that on purpose because the surface is almost flat. It is concave, but it's almost flat. It's approximately flat. So all those formulas that we're using is based on this approximation. So here you go. You know, as we approach the center of curvature of the mirror, the image is formed at the same point where the object is located. Right? Now think about that. if an object that's very far away produces an image that's very close to the focal point, right? What happens to an object that is located at the focal point? Also, what happens to the image of an object that's located between the focal point and the center of curvature? The size of the image becomes larger, right? See that? Further away from the radius of curvature, the size of the image is smaller. At the curvature of the mirror, the size of the image is the same. As you get closer and closer to the focal point, the size of the image becomes larger and larger. Okay, I'm going to decrease the size so it can fit here in the screen. Now, if an object that's very far away has its image at the focal point, what happens if the object is exactly at the focal point? You know, if the object is exactly at the focal point, the image is very far away, is formed very far away. Okay, see those two light rays? I drew that in they are parallel to one another. That's what we call an improper image. Between the focal point and the surface of the mirror, the image becomes improper. And the image is seen on the back of the mirror. Okay, so here you go. The light rays diverge in the left direction, but they converge towards the right of the mirror. See light ray, all the three light rays here, right? 1, 2, and 3. So let's summarize what we have here. Let's summarize what we have here, right? So, summarize what we have here. Summarizing what we have here. Here, 1. Object located very far away from the mirror. And what does it mean, very far away from the mirror? It means that P is much greater than the focal point. Okay? P much greater than the focal point should be, considered greater than 10 times F. Okay? Object located very far away from the mirror. Image is formed at the focal point. Near, not at the focal point, but near the focal point. No. Practical examples. Practical examples. The case of a star, of the sun, of the image of the sun and the stars. The telescope. They are formed very close to the focal point of the telescope. So if you play this telescope, you should know that, right? What's next? 2. Object located between the radius of curvature, radius of the point of curvature of the mirror, point of curvature of the mirror. Mirror. Object located past the point of curvature of the mirror. Image is for, okay, let's go back to our, here you go, past the point of curvature of the mirror. Here you go. Image is formed between the focal point and the point of curvature. Image is formed upside down between the focal point and the point of curvature of the mirror. Okay. Object located at the point of curvature of the mirror. You know, what else? Image is smaller than the object. It's still upside down, Object located at the point of curvature of the mirror. Here you go, I'm gonna copy and paste here. At the point of curvature of the mirror. Image is formed upside down at the point of curvature. At the point of curvature. The point of curvature of the, we don't need to write this one, right? Because I already put upside down here. Object located between the point of curvature and the focal point of the mirror. Let's go, let's take a look here. And everything here you go. Same size between the focal point and the point of curvature of the mirror. Image is formed upside down past the point of curvature. Image larger than object. Okay. Image size equal to the object size. Okay. Am I sharing the screen? I am, right? Good. Someone has to mute. What else? Object located at the focal point. Right? At the focal point. Now we'll put the object at the focal point right in here. Okay. Image is formed at a very distant point from the mirror. Image, okay, from the mirror. From the mirror. Image is considered improper and should be infinitely large. Okay. Did I do that? Let's do that. Let me see if I did that. Yeah, I did that here. Okay. Magnification, here you go. 1 divided by I, 0, right? And the magnification. Yeah, magnification should be infinity as well, right? Because the image is being formed at infinity distance. You plug in here, you have infinite magnification, but the image is considered improper. It should be infinitely large. okay, this type of image also is called, you know, real image, okay, real image, because it can be projected on a piece of paper, real image, okay, real image. Here the image is improper. Now at point 6, you know, object located between the mirror surface and the focal point of the mirror. Okay, so let's take a look here. Now at this point, now we start to form our virtual image. Okay, virtual image. Image located between the mirror, object located between the mirror surface and the focal point of the mirror. Image is formed behind the mirror. The image is said to be virtual. This image is said to be virtual. Okay. So those are the 6 cases, right? Let's substitute that in the equation here. Here you go. What if P is less than F, right? Let's say P is F divided by 2. Right? What happens to this case, for instance? We're gonna get minus equal. The result is a negative number for the position of the image. The negative number means that the image is virtual. Positive number means that the image is real. Okay? That's what we get. So here you go. Let's put C, no, not C. Let's put B. Okay? B greater than 1. B greater than 1. And now we have here B. 1 minus B. Right? 1 minus B. And you have F to be more genetic, right? B minus 1. B minus 1. Less than 1. Less than 0. Image is virtual. Is formed behind the mirror. Okay. What about the magnification? Let's take a look at the magnification. Equation for the magnification right in here. Nope, not this one. This one here. Let's put like divided by B, right? So you can see that more clearly. B is greater than 1. And now we put the B right here upstairs. Okay. Let's see. Do I have it? No, I missed the copy. Let's copy it again. Magnification. That's the magnification. right? For this specific case, we are going to get this relation. The negative sign cancels out. See that? Negative cancels out with negative. Right? P is going to be less than the focal point. Let's put here F divided by B. Okay. Becomes BF. Okay, and F cancels with F. And we get this number. And we get this number that's greater than 1. Right? B is greater than 1 as well. So what does it happen? What happens that not only object between the mirror surface, focal point mirror, image formed behind the mirror. This image has to be virtual. The image is larger and formed behind the mirror. This image is said to be virtual, okay? I am virtual because I is less than 0. Those are the 6 different cases that you can derive from the equation and do all that simulation that you saw, okay? What about, now you gotta repeat the same thing for convex mirrors. Repeating the same for convex mirrors. Okay, so let's go to the simulation here. Let's see, mirror, lens, converging, diverge. No, that's lens, mirror. Okay. The divergent lens, the convex lens, you can relocate my object here on the other side of the mirror. Make sense? That's what the simulation is all about. I'm going to adjust this focal point so it coincides exactly with this coordinate 2. Let's see how we draw the ray tracing diagram, right? But before we do that, just take a look what happens. It's much simpler. It's a much simpler situation, okay? Here you go. The image is always smaller, you can see it, than the object. Okay? Always smaller than the object. So it's much simpler than the case, and the formation of the image is restricted between this region of the mirror and the focal point. Okay? So let's see how we do that. So let me this is still convex mirror. Here you go, concave mirror. Now we're gonna do convex mirror. Oh, I don't have convex mirror here. Oh, what a shame. I don't have convex mirror here. Okay, so I have to do that from scratch. Let's do that from scratch. Procedures is very similar. Okay, so here you go. Now instead, let me copy and paste. Okay. Let's see here. Okay, axis of the mirrors. No. Okay, let's copy that. This one that we have to copy. Axis, point of curvature, focal point, right? All the sorts of We're going to repeat that now for a convex mirror, which is almost the same, but it's simpler. You know, instead of a convex mirror that has a bulge, right, is represented in this way. Okay, we're gonna get, just like before, we're gonna get the axis of the mirror. I don't need that anymore. I'm gonna get the point of curvature of, oh, let's see here. No, this one here. The point of curvature of the mirror. Focal point of the mirror. Here you go. This one we actually call the C prime, okay? Because it's not the point of curvature of the mirror. The actual point of curvature of the mirror is to the right. If I have it the right distance, let me check here. Let's make sure we have the right distance. Grid lines, yep. I'm gonna move this guy a little bit to the right. Yeah. No, I'm gonna move a little bit to the left, so I have some space on the right. Let's go a little bit more to the left. Here you go. Now I'm changing the position. I will put my focal right in here. And I will copy and paste on the other side. But here should be the center of curvature of the mirror. I'll call this one the actual center of curvature of the mirror, right? Let's see, yeah, because this mirror has a curvature in this direction, right? Okay, so let's start from scratch. I'm gonna take this one out, just play the, right? Start with this image. The next image is going to be the axis of the mirror. Oh, wow, here you go. This one. Here you go. The points of curvature of the mirror. Here you go. This one. We don't need that. Don't need. Yeah. Gonna get those two here. Yeah, I don't want that. I want just the axis. Okay, here you go. Oh, gotta put the right order. Here you go. Now I'm getting the right order. I'm going to delete this one here so I don't get lost. Here you go. One, another one. Here you go. Mirror, axis. You know, center of curvature on the right. Right? Center of curvature on the right, center of curvature on the left. Those are points that are symmetric. And then I'm going to position my mirror, my object. The next step is position the object. Don't need that. Here you go. I gotta get this object here. What time is that? 15 more minutes to go. Position my object. Let's position my object a little bit further away, right in here. And go. We're getting there, right? Mirror, axis, points, center of curvature, and the focal points, and they're symmetric. Object. Okay. And now the distance of the object to the mirror. I'll get that. Here you go. Oh. Of the object to the mirror. I don't need that anymore. What about the light rays? What about the light rays? Okay. So here you go. This image, the object is to the right, right? It's not going through, this one is not going through the center of curvature, so you don't have to worry about that. So let's do the image that goes through the focal point. Here you go. See the image that goes through the focal point. Image the light ray that goes through the focal point, right? Goes right in here. The light ray that goes through the focal point is reflected parallel to the axis. Now let's get this. Well, let's do this one first. Light rays parallel to the axis is reflected through the focal point. Okay. Next. And then we must have the light ray that goes towards the focal point. Oh, no, don't do that. Copy and paste. Here you go. That goes through the focal point, is reflected parallel to the axis. That should be enough for us, but we can go for another. I'm gonna change the color of those two light rays to red. We usually draw this line here that's past the mirror. We draw it as a dashed line. Okay, here you go. Here you go, like that. So to emphasize that this light ray is aimed towards the focal point on the other side of the mirror. Okay, and what else? We have this other light ray. Well, we can have the other light ray as well, right? Go. Let me erase this one. Erase this one. Let's see this one. Hey, let's use those light rays. That's better, right? And Here you go, this green ray. And then we should have this green ray that's incident at the center of the mirror. And it's reflected at the same angle, right? And then how do we form the image? The next question is, how do we form the image? Okay. Okay, the image is formed by extending, by intersecting the points of the extended reflected light ray. Okay, so here you go. I'm going to extend it. This one here is going to intersect right in here. I'm going to extend this light ray, and it should be, intersect right in here as well. So now we have our image that is upright and smaller. Let's get it. It's thinner. Okay, here you go. That's the image that's formed. And there is only, one case for that. You have a virtual image all the time, no matter what is the position of your object. And the magnification is always less than 1. Okay? So even though it seems to be a more difficult type of problem, it has a simpler result than that of the concave mirror. Any questions about that? Let's see. No questions. Let's take a look at the, here you go, this one. Yeah, this one right in here. 150, we have 10 more minutes to go. Okay. By the way, the equation for concave mirrors is the same. Convex mirrors is the same. For the same. The equations are the same. Work. Like that. Here you go. Spherical mirrors. Go. And then we have a table. Let me take a look at my own notes too, because I also have a table here somewhere. Let's see. Okay, quantity object, positive object in front of the mirror. Real object. We may also have a virtual object. We're not covering that. Well, there's too much stuff. Okay. Image is in front of the mirror. Real image. Q. You know what? I, right, in your book is I. Is positive. Focal distance is positive when the mirror is concave. Is negative when the mirror is convex. H prime is positive when the image is upright. Is negative when image is inverted. Okay. Magnification is positive when the mirror is upright. The image is upright. It's negative when the image is inverted. So those are the cases for mirrors. There are some examples here. And what comes next is lenses, okay? And we use lenses, and it behaves quite in the same way as mirrors, and even the equations are the same, but only for thin lenses. So here you go. Next, Next is thin lenses. I think we can stop here because it's gonna take some time to cover lenses, but it behaves much in the same way as a mirror. Let me show you before we leave. Let me show you the simulation that we have here. Lenses, right? Mirror lenses. Here you go. We have converging lens and diverging lens. Okay, why it doesn't? Oh, here you go. Diverging lens and converging lens. Converging lens, the lens is convex. Okay, here you go. Important difference between mirrors and lenses. Okay, a thin lens. Converging lenses are convex. Converging mirrors, which means converge the light, are concave. You know, exactly the opposite, right? And then you have the opposite also for diverging. Diverging mirrors are convex. Diverging lenses are concave. And that's what we have here. Here you go. This lens is converging. You can position the image very far away from the lens. If you position the image very far away from the lens, then the object very far away from the lens, then the image is formed at the focal point, right? If I decrease, right, the focal point, you can see the image gets closer and closer to the focal point behind it. Okay, those lenses are considered not only thin, but they are also considered spherical lenses. As I approach the object to the point where is the center of curve, twice the focal point, just like in the case of a converging mirror, the image is upside down and has the same size and also has the same distance. It formed from the same at the same distance than the object, right? Here's 2f and here's 2f. As I approach the focal point of the lens, the image grows larger and larger and further away from the center, from the point of 2f, right? At exactly the focal point, just like we have for the mirror, the image that's formed is improper. The difference is that the image is formed on the other side of the lens, right? So here you go. That's another difference between mirrors and lenses. Converging mirrors are concave. Differences. Converging mirrors are concave. Converging lenses are convex. Right? Converging mirrors form real images on the same side as the object. Okay. Converging lenses form real images at the, let me see, at the same side, at the other side of the lens. At the same side of the mirror, right? Let's see, converging mirror from an image on the same side of the object. Right? Converging lenses form real images at the other side of the lens. Okay. What about converging mirrors form virtual images on the other side of the mirror? Converging lens form virtual images on the same side of the object. Those are the differences that are exactly opposite. But what are the similarities? Seen lenses, seen spherical lenses. Let's put spherical, let's characterize spherical lenses. What are similarities? Same equations. Same equations. Okay. So here you go. So we have this improper image, and here you go. Now we are forming the virtual image here on the left side. Let me decrease the size because this guy is humongous, right? It's huge. Okay. So in this case, the ray is going through the center of the lens without any deflection. The light ray that's going parallel is convert towards the focal point. Okay, so it's it's a similar behavior. Okay, and we'll talk more about that next time because we're running out of time here right now. 1:59. So any questions? Okay, so I see you tomorrow, and if you wanna stay for office hours, I'll be here for the office hours.
Thank you,
Okay,
Professor.
thank you for being here.
Professor, I have questions about the Excel.
Okay, what's your name?
Harun.
Harun. Okay, let me get some water. Okay, hang in there.
Okay.
It's Thursday here.
Thanks, Prof.
Okay.
Good tomorrow.
Hot here as well. Okay, so I'm back here. Let me stop the recording.